Let's do passage 3 now. Passage 3 says students studied forces by using two identical platform scales, scale A and scale B, one of which is shown in figure 1. So in figure 1, we have a scale. It has a nice platform, dial, and table. So the dial shows you the amount of weight on the platform. We have a hand pointing to 0 because right now there's no force on it. If we exert some force on it, as shown here, we see the hand moves. So there's a weight that's greater than 0. The weight of the platform of each scale was insignificant, and when a force, such as that produced by a weight, was exerted on the surface of the platform, the hand rotated clockwise away from the 0 point on the dial. The amount of rotation was directly proportional to the strength of the force. So that means that no matter what, the change is going to be directly related to the amount of weight exerted on the scale. So if we change it by x, the dial might rotate by y. And then if we increase the weight to 2x, right, so we're doubling it, then we're going to do 2y of the distance of the dial. So study 1 says prior to each of the trials 1 through 3, the students set the dial readings of the scales A and B back to 0. So they're starting at 0 every time, so we don't have to worry about that, which is nice. In each of these 3 trials, scale A was stacked on top of scale B. See figure 2. So this is figure 2. And in trial 1, there was no weight, so this is just empty. In trial 2, a 5 Newton weight was placed on top, and in trial 3, a 10 Newton weight was placed on top. And the dial readings for the 3 trials are also shown in figure 2. So we see the figure 2, right? So with this one, with just the scale on top of it, this is showing 0, right? Because there's no weight on top. And here there is the scale on top, so it's showing about quarter wave movement. Here with 5 newtons, we're seeing an increased change. And with 10 newtons, we're seeing that this one is going all the way halfway, and this one is going halfway plus a quarter. So study 2 says the students placed a pencil on the platform of each scale and positioned on the top of the pencils a board that spanned the 0.40 meter distance between the 2 scales. Prior to each of the trials 4 through 6, the students set the dial readings of scales A and B to 0. So we see they're both at 0, they're 0.40 meters apart, and there are pencils holding them up. And the reason we have to set it to 0 is so that we can actually consider the weights of the blocks and not just the weights of the board and pencils, because that's a significant amount of weight to toss on there. So let's look at our results. So in each of the trials, a 10 Newton weight was placed on the board at various distances from the pencil on scale B, so right away over here. So in trial 4, the weight was 0.1 meters from the pencil. In 5, it was 0.2 meters, and in trial 6, it was 0.3 meters away. So if we look, we have a change here. First, it starts with not a lot of change on this side because the block is really close, so this is a bigger change. And then it looks about 50-50. And then for this last trial, it looks like there's a lot more weight here, which makes sense, right? The block is closer to that scale. So let's answer some questions. Question 13 says, in which of the trials in study 2, if any, was the force on the 10 Newton weight equally distributed between scales A and B? So we don't even need to consider any physics, right? You could go the physics route and say, well, we want the one that's closest to the middle, and we know it's going to be 0.40 meters, and that 0.40 divided by 2 is 0.20, so that probably means that it's going to be the center one, which is trial 5. And trial 5 is the correct answer, so that does work. But an even easier way to do that is to look directly at the information we've been given. So if we look, right, we don't even need to consider any physics. These two, they're not equal, right? This one is high. This one is not high, actually. This one is low. This one is high. These two are equal. That's good, right? We want them to be the same because we were looking for equal distribution, right? Equal value. This one is high. This one is low. That means it's going to be trial 5. That's B. Question 14 says, based on the results of trial 1 and 2, scale A and B each way. So let's look at trial 1 and 2, right? So if we look here, if you put the scale on top of another scale, so this scale B down here is only reading the weight of scale A, right? It's going to go about the quarter of the way. So a quarter of the weight is equal to the scale. And now if we look here, if you put a 5 Newton weight on top of the scale, it also goes a quarter of the way. So that means a quarter of the weight is equal to both the weight of a scale and a 5 Newton weight. And of course, a 5 Newton weight weighs 5 newtons. That means the scale, because it also pushes the dial to a quarter of the way, needs to equal 5 newtons. Question 15 asks, assume that whenever a weight was placed on a scale's platform, a spring inside the scale was compressed. Assume that the greater the added weight, the greater amount of compression, right? So we have a scale inside the scale. We have a spring. The more the spring is compressed, the higher the weight, and that's how it reads the dial. So was the amount of potential energy stored in scale A's spring greater in trial 1 or trial 3? So here it's saying the amount of potential energy stored in scale A's spring. So potential energy of a spring comes from its compression. So the more it's compressed, the higher the value of the potential energy. And the more it's compressed, that means there's more weight. So we're looking for a higher value, right? So it's saying, is the amount of potential energy, the amount of compression higher in trial 3, where we have a 10 Newton block and a scale on top of scale B? Actually, sorry, we're only considering scale A. So we're considering scale A, so don't worry about scale B. Right? So we have a 10 Newton block on top of scale A here, right? And nothing on top of scale A here. And it's saying which one has a higher rate of compression of the spring. So we want a higher weight, and there's a higher weight on top of scale A in trial 3. Let's look at our options. All right, so we definitely want trial 3 because there's definitely more weight on the scale during trial 3. So trial 3 says because the amount of weight on this platform was greater in trial 3. So that's true. Let's check D just in case. It says in trial 3 because the amount of weight on the platform of scale A was less in trial 3. And it wasn't less, it was more. So that's not correct. Question 16 says, in a new study, suppose scale A was placed upside down atop scale B so that the platform of scale A rested directly on the platform of scale B. Which of the following drawings best represents the results that would most likely be obtained for this arrangement? So if we're looking here, right, the scale on the bottom is easy, right? It's straightforward here. There's a scale on top of it, and that's all we care about. The spring is only being compressed by one scale. And if we remember from right here, right, 5 newtons is 1/4, right? So if we have a scale on top, all we need to move is 1/4. So that rules out G and J. Now we need to look at the scale on top. So if you think about the scale on top, right, the way that the scale actually works, let's look up at this drawing, is that the spring being compressed is the only thing that matters in terms of how it measures weight. So it doesn't actually, so if it's upside down, it's still going to feel the weight of the scale itself. So the spring is being compressed by one scale, if that makes sense, right? Because the platform is being pushed down by the weight of the entire scale. And we know the weight of the entire scale, right? We found out before that it was 5 newtons. So if the weight of the scale is 5 newtons, that means it should be compressed 1/4 of the way. Now, the only other note here is that the scale on top is upside down. So if the 0 is up here, then 1/4 of the way is going to be facing this way, which gives us option F as our answer. Question 17 asks, the main reason why pencils were placed on the scales in study 2 was most likely A, so that the line of contact between pencil and its platform could be used as a reference line for distance measurements. So that one's pretty legitimate, right? Like if we look at all the distance measurements here, it does look like we're using the pencils, yeah. So that looks pretty legitimate. Let's check it off, but let's look at the rest just in case. Question B, option B says, so that the board would roll from side to side rather than sliding from side to side over the scales platforms. So we never actually move either of the platforms in any of these cases, so it's probably not going to be B. Question C says to add additional weight to the scales. So we don't actually care about the weight of the scales. In fact, we zero them out after we go through the actual thing. So that one's probably not going to be the case, right? We don't care about the weight of the pencils or the boards or anything like that, and we don't need to add additional weight to the scales. They're fine even with no weight. So that one's not true. And D says to provide extra room for air above each scale's platform so that the air pressure would be the same above and below the platform. So this one's also not true. Sometimes options like this can be misleading because they sound right and they would make sense, maybe, perhaps, right? They have lots of big scientific words in them, but it's important not to get distracted by them, right? You've been given a certain amount of information, and while the ACT Science does assume you have some basic knowledge, it's not going to ask complicated questions like this. Oftentimes, they want you to take the information they give you and draw inferences from it. Yes, sometimes you need to know information like what pH is or what a force is, but they're not going to expect anything that's complicated. Question 18 says, in study 2, as the distance between the 10 Newton weight and the pencil on scale B increased, the amount of force exerted on the surface of scale B's platform, blank. So in study 2, right, we changed the distance between the pencil and the block. And we're saying as it increases, right, what happens to the force? So as the distance increases, so as it gets farther away, what happens to the force? And once again, we don't need to think physics here, right? We can just look at the dials on each of these scales. So if we look here, this one, it's really close. We have a really high force, right? Here, it's right in the middle. We have a lower force. And then here, it's far away, and we have an even lower force. So that means that it decreased only, right? It consistently decreases. Something like varied, but with no general trend, again, can be tempting, but you want to try and stick to exactly what you saw. I know the word only can be scary, but at the same time, trust your gut, right? They decrease every single time, so it decreased only. Question 19, it asked, which of the following statements most likely describes an important reason for setting the dial reading on both scales to 0 after study 1 prior to each of the trials of 4 through 6? So our options are to add the weights of the scales to each weight measurement, to add the weights of the board and pencils to each weight measurement, subtract the weights of the scales from each measurement, and to subtract the weights of the board and pencils from each weight measurement. So if you remember from before, we're actually considering the weight of the platform to be negligible, and we're not putting any scales on top of each other. So A and C are not going to be relevant, right? We're talking about the board and pencils. So if you look at this right now, we're seeing for adding or subtracting the weight of the boards and pencils to each measurement. And because each measurement, if you look up here, doesn't account for the board and pencils, we're actually trying to get rid of it here. So if we count including the board and pencils as 0, we're effectively subtracting it from our weight. So let's go with D. Overall, this passage is definitely a challenging one, but one big factor about it is that it looks more challenging than it actually is. It looks like it's going to have a ton of complicated physics equations. We have scales stacked on top of each other, weights in newtons. It's a lot of different things going on at once. With questions like this, it's really important to break it down into what it actually means. And you don't want to spend too much time going through the passage, but there's nothing wrong with taking some quick notes, right? You get to write in your test book for a reason. That's an important part of ACT science. And also, if you're unsure, just dive right into the questions. Many of these questions could be answered even if you only understood one part of the graph. Thanks.